The impossible question. Have you ever wondered what would happen if humans could create a black hole on Earth? What if somewhere in a laboratory, deep underground, scientists were already doing it? Not metaphorically, not a simulation, but a real functioning black hole analog that bends light, swallows energy, and mimics the most powerful force in the universe. It sounds insane, right? A black hole is the ultimate cosmic monster, a gravitational beast so intense that not even light can escape. The idea that humans could build one sounds like the plot of a sci-fi disaster movie. But here's the twist. Scientists are actually doing it, not to destroy the planet, but to understand the universe itself. So, how do you build something that defies physics itself? What happens inside these secretive labs where black holes are being born? Not in space, but in vacuum chambers and supercooled circuits. And most importantly, could we lose control? Let's go inside the lab. The birth of an impossible idea. The story begins not with a telescope, but with a chalkboard. In the 1970s, physicist Stephen Hawking proposed something revolutionary. Black holes aren't completely black. They emit faint radiation, now called Hawking radiation, that slowly causes them to evaporate. The only problem? Nobody had ever seen it. It was too faint, too far, too theoretical. So a few bold scientists asked, what if we build a fake black hole? Not one that destroys galaxies, but one that mimics its behavior. Something that behaves mathematically, like a black hole, but safely here on Earth. The idea gave birth to what physicists now call analog black holes, systems that reproduce the same equations and effects, but using sound waves, light, or even ultra-cold atoms instead of gravity. In other words, they wanted to bring a piece of space-time into the lab to study the most mysterious object in the universe without, dying. But how do you even begin to build a black hole? The acoustic black hole. The first successful attempt didn't use space, light, or even gravity. It used sound. In 1981, a physicist named William Unruh made a radical proposal. He realized that if you force fluid to flow faster than the speed of sound, something incredible happens. Sound waves inside the fluid can't escape upstream, just like light can't escape a black hole. He called it a sonic black hole, or more technically, a dumb hole, because no sound escapes. Get it? Imagine a river speeding up as it falls over a waterfall. At a certain point, the flow becomes so fast that sound waves trying to move against it are dragged downstream. That point of no return acts exactly like an event horizon. Unruh's idea sat quietly for decades, theoretical, beautiful, but untested. Then in the 2000s, physicists began turning it into reality. They used ultra-cold atoms, called Bose-Einstein condensates, cooled to just billionths of a degree above absolute zero. These atoms behave like a single superatom, where quantum effects become visible on a macroscopic scale. By controlling the flow of these condensates with lasers, scientists created regions where the speed of the atoms exceeded the speed of sound inside the medium, forming an acoustic event horizon. And when they measured the sound wave, they found something unbelievable, a faint hiss of thermal radiation exactly like Hawking predicted. They had built the first black hole analog, and possibly the first hint of Hawking radiation on Earth. Black holes made of light. But sound isn't the only medium that can bend and trap things. Light can too. Around 2010, physicists started experimenting with something called optical black holes. Instead of using gravity, they used materials that manipulate how light moves, known as metamaterials. These materials can slow down light or even bend it backward. By designing a medium where the refractive index changes dramatically, scientists created a region where light can't escape, an optical event horizon. Think of it like creating a small patch of space where photons get stuck. They can enter, but they can't get out. In one famous experiment, researchers at the University of St. Andrews in Scotland used a fiber optic cable with a moving refractive pulse. When they sent another light signal behind it, that light was trapped, forming an artificial event horizon. For the first time, we could watch light behave as if it had crossed a black hole's boundary right there in a lab. And then came the next bold question. Could we make one emit Hawking radiation, just like the real thing? In 2019, a team in Israel did exactly that. They built an optical system that emitted a faint thermal spectrum matching Hawking's predictions. The radiation wasn't coming from gravity. It was purely from light behavior. Yet the pattern was unmistakable. It wasn't just tricks of physics. It was evidence that the mathematics of space-time could be recreated on a tabletop. Inside the superfluid horizon. But sound and light were just the beginning. The real magic happens in superfluid quantum materials that behave like fluids with zero viscosity. In these systems, particles move collectively, almost like dancers in perfect synchronization. They can flow endlessly without losing energy, and that's where things get weird. Physicists discovered that within a superfluid, if you rotate it fast enough or create a flow gradient, you can form regions that behave just like the warped fabric of space-time around a black hole. In 2017, researchers at the Technion Institute in Israel and Laval University in Canada created a superfluid vortex that mimicked the swirling gravitational pull of a rotating black hole, a Kerr black hole analog. These weren't just simple copies. They showed frame-dragging effects, the same phenomenon Einstein predicted, where space itself twists around a spinning black hole. The implications were staggering. Inside these quantum vortices, scientists could now study how space-time behaves, when it's twisted, stretched, and torn apart, all without ever leaving Earth. In a way, they weren't just watching the universe, they were rebuilding it. The quantum puzzle of Hawking radiation. Let's pause here for a moment, because this is where things get deep and weird. Hawking radiation is one of the most mysterious ideas in all of physics. It says that black holes slowly leak energy through quantum effects. Here's how it works. Near the event horizon, particles constantly appear and annihilate in pairs, a particle and its antiparticle. Usually they cancel each other out instantly, but near a black hole, gravity can separate them. One falls in, the other escapes. The escaped one becomes radiation. The one that falls in subtracts from the black hole. Over time, it evaporates. But there's a catch. We've never seen this radiation directly in space. It's too faint to detect. That's why the lab experiments are so revolutionary. If they can recreate even the signature of Hawking radiation, they can confirm one of the most profound predictions in physics. And indeed, that's what's happening. In 2019, Jeff Steinhauer's team at the Technion reported observing pairs of sound waves, phonons being created at the acoustic event horizon. One inside, one outside. The distribution matched Hawking's thermal prediction almost perfectly. For the first time, humans had watched quantum radiation from an artificial black hole. Let that sink in. We recreated the physics of the universe's most extreme object, not in space, but in a glass chamber on a lab bench. The danger question: could it go wrong? Now, the obvious question: are we insane? If you can create a black hole, even a fake one, could it accidentally become real? Some feared that experiments at CERN's Large Hadron Collider might create microscopic black holes that could swallow the planet. The media went wild. Lawsuits were filed, but physicists remained calm, because even if microscopic black holes formed, they would evaporate almost instantly due to Hawking radiation. And so far, they were right. No disasters, no mini singularities hiding in Geneva. The artificial black holes made in labs aren't gravitational at all. They just simulate the same equations. They bend sound, light, or quantum fields, not space-time itself. In other words, they're safe. but that doesn't make them any less mind-blowing. These analog black holes let scientists study cosmic mysteries in controlled conditions, revealing clues about information loss, quantum gravity, and even the nature of space-time itself. The lab black holes can't destroy us, but they might destroy our understanding of what reality really is. Information, paradoxes, and secrets. Every artificial black hole also brings us closer to solving one of the greatest paradoxes in physics, the black hole information problem. Hawking's theory suggests that black holes eventually evaporate completely, but if they vanish, where does the information about what fell inside go? Quantum mechanics says information can never be destroyed, but general relativity doesn't agree. That contradiction has haunted physics for 50 years. By building analog black holes, scientists can now watch how information might behave at an event horizon, whether it leaks out, scrambles, or disappears. Some experiments even suggest that quantum entanglement plays a key role, the same phenomenon that Einstein called spooky action at a distance. The radiation emitted by these analog horizons might carry hidden correlations, a hint that information isn't lost at all. We're still a long way from solving it, but for the first time, we can test it in real systems instead of chalkboard equations. The race to create gravity in a box. While most analog black holes use sound or light, there's a new frontier emerging, simulating gravity itself. At Stanford University, researchers are creating synthetic spacetimes using quantum circuits made of superconducting qubits, the same technology used in quantum computers. By programming how information moves between these qubits, they can recreate the mathematical behavior of curved spacetime, including event horizons, wormholes, and yes, even black holes. In 2022, a team at Google and Caltech simulated a baby wormhole on their quantum computer, a structure that connected two regions of entangled quantum states, behaving mathematically like a miniature space-time tunnel. This wasn't science fiction. It was real quantum data behaving as if it were space itself. Now imagine pushing that further, not just simulating a black hole, but letting it evolve, radiate, and interact. The dream is to eventually have a quantum space-time emulator, a system that recreates the laws of gravity in a controllable, testable form. It's like having a miniature universe running inside a fridge-sized computer. The philosophical earthquake. Here's the part that blows the mind of even the most hardened physicists. If we can build artificial black holes that obey the same laws as real ones, what does that say about our universe? Are we ourselves living in an analog system, a cosmic simulation where space-time behaves according to deeper mathematical rules? When we build a black hole in a lab, are we creating a new layer of simulated reality within a universe within a universe? Some philosophers argue that this changes everything, because if physics can be reproduced, it might mean reality is fundamentally computational. Others see it differently. They say this work doesn't cheapen the universe, it honors it. By building artificial black holes, we're not playing God, we're decoding his equations. Either way, the implications are cosmic. We've gone from watching black holes through telescopes to building them with lasers and circuits. And with every step, we get closer to answering the oldest human question: what is reality made of? The next generation of black hole builders. Right now, all over the world, teams of scientists are racing to push this further. At the University of Nottingham, researchers are building analog gravity systems using fluid surface waves in water tanks that mimic the behavior of black hole horizons. In Japan, teams are experimenting with plasma vortices that twist electromagnetic fields into relativistic configurations. In Switzerland, researchers are designing superconducting networks where information flow behaves like energy falling into a black hole. Each of these systems tests a different piece of the cosmic puzzle, and together, they're helping us map the physics of the universe's most extreme phenomena. The labs are quiet, cold, and precise. But make no mistake, these are the new event horizons of human knowledge. Every hum of a laser, every flicker of a photon in a vacuum chamber brings us closer to understanding the machinery of the cosmos itself. A universe in a test tube. Here's something poetic to think about. A black hole, the most mysterious object in space, is also one of the simplest, defined only by its mass, spin, and charge. Yet it holds the keys to understanding everything from quantum mechanics to the fate of the cosmos. Now, inside laboratory chambers, physicists are replicating that same simplicity. A vortex of atoms, a pulse of light, a flow of sound. Each one is a tiny universe, a test tube cosmos where gravity, time, and energy dance in miniature form. It's humbling, because for all our technological progress, what we're really doing is listening to the whispers of the universe, replaying its song in our own instruments. The notes are the same, just played on a smaller stage. The final paradox: who's watching whom? Let's end with one haunting question. If humans can build artificial black holes that simulate the laws of the universe and use them to study how reality behaves, then what if someone else did the same thing, billions of years ago? What if our universe itself was born from a cosmic lab experiment, a higher dimensional simulation studying its own black holes? And if that's true, what happens when we turn on ours? Are we the scientists, or are we the experiment? The new frontier of creation. Artificial black holes aren't just a scientific curiosity. They're a doorway not into destruction, but into understanding. By recreating the universe's most extreme objects, we're unlocking the secrets of space, time, and quantum reality. We're probing the boundary between the known and the unknowable, between experiment and existence. It's not about conquering nature, it's about speaking its language. Every analog black hole, every faint hiss of Hawking radiation, every photon trapped in a light horizon is telling us one thing. The universe is not beyond our reach. It's inside us, inside our equations, and now inside our labs. We are the only species that looks into the abyss and decides to build one. And that's not madness. That's curiosity, the most powerful force in the cosmos. So next time you look up at the night sky and wonder what lies inside those black holes, remember, somewhere on Earth, in a quiet, glowing lab, humanity is already finding out. And that's where the story of creation continues. Stay blessed and stay curious.